Can you all see my screen?
Yep.
Awesome. Thank you so much. So, hello everyone. Welcome to the IUPAC WorldFAIR Chemistry virtual webinar series. This is our first webinar in this series titled, What is a Chemical? And regarding handling chemical data across disciplines. My name is Fatima Mustafa. I am the project coordinator and I'll be hosting this event along with my colleagues, Leah McCowan, Stuart Chalk, and actually Ian Bruno, who will be moderating the discussion in this session. So thank you everyone for joining from different time zones. Thank you so much for attending so far. And thank you for our great and amazing speakers who actually accepted this invitation to be with us today. So thank you. Let me briefly introduce you to our agenda for today's webinar. We will be having the first part of it, which is a flash talks moderated by Ian Bruno. We will be having the 7 amazing speakers who joined us to talk about their how they handle chemical data in their disciplines. As you can see here, we have diverse topics of covering the environmental science, the science, the astrophysics, and the material science as well. After that, we will be having a panel discussion where all of you are invited to submit your questions in the Q&A the panel. And we hope that all of your questions will be addressed by our speakers. Before you leave, we would love definitely to have your feedback about this event. And if you would like to be also participating and engaging with us, we have a couple of volunteering opportunities, as well as we have some reminders and announcements for you. So please stay tuned with us until the end of this 1 hour and a half. All right, so before we start and we have the talks that we were talking about, let me just here introduce you to the IUPAC and the WorldFAIR project, which actually this webinar is brought to you by them. So the IUPAC is the International Union of Pure and Applied Chemistry. It is the authority of nomenclature, terminology, and standardized method of measurements. Not only the IUPAC is engaged in this effort, but also it's engaged in many wide-ranging activities, speaking about, for example, publishing technical data, journals, book databases, as well as organizing symposia, conferences, and honoring a scientific contribution as well. Also, the IUPAC is highly involved in other projects that impact the professional chemistry as well as the community in general. One of those events could be the digital, one of those, let's say, project is the digital IUPAC, which I will explain a little bit about it later. And something to know about the IUPAC, it has many committees, divisions, and it's also the mechanism work, it's a project-based, so anyone in the entire world could propose any project and it could be approved and started being worked on later. So our project is, let's say, is mainly led by the CPCDS committee, which led by Leah McCowan. So one of the things that IUPAC is focusing on since many years now is the digital IUPAC. So IUPAC is trying to translate the chemical communication into a machine readable, let's say, or digital domain. For that, we have 3 main pillars. The first one is the chemical concepts and definition, where chemical terms are transferred into machine readable readable formats. Also, the chemical structures and notations and data and metadata also we try to develop a machine readable format for that as well as the third pillar, which are all of the critically evaluated other data, you name it, spectral data, solubility data, etc., etc. The main goal of the digital IUPAC is to develop machine processable technical description building on the IUPAC authoritative scientific definition. As I mentioned earlier, so this webinar series coming to you through the collaboration between IUPAC and the WorldFAIR project, which is a new global initiative to advance implementation of the FAIR data principles. When I say FAIR, it means, I think most of you probably are aware of it now, or if you are not, it's fine. So it's a new term, I guess, started in 2016, means to have the data findable, accessible, interoperable, and reusable. This project came as a partnership between the CODATA as well as the Research Data Alliance. As I mentioned, to advance the implementation of the FAIR data principle, to create a framework for FAIR assessment, and this also bring an engagement between a cross-domain interoperability framework. That's why this project actually include 11 cases. As you can see here, we have the geochemistry, nanochemistry, social science, biodiversity, agriculture, biodiversity, chemistry, and so on. And chemistry, as you can see here, is one of those cases, and it's led by the IUPAC. Our project, as you can see here, as I mentioned, is led by the IUPAC, particularly by the CPCDS committee, led by Leah McEwen. We have set up three main, a set of deliverables, I would say. Those deliverables are handled by subgroups or sub-projects of the main entire project. So we have the first project is called FAIR Chemistry Data Guidance, which is led by Ian Bruno, our moderator for today. Which we are trying over there to create a guidance for FAIR data implementation for stakeholders such as publishers, researchers, funders, and you name it. The second subgroup is the FAIR Chemistry Data Cookbook, which is led by Stuart Chalk, who is also with us today, which we were trying to develop a cookbook or that include recipes to help in depositing machine-readable data. The third group is the FAIR Chemistry Data Protocols, which is led by Evan Bolton, and we're trying here to develop browser-based services that help in checking the machine readability of chemical data as well. So thank you for all of our collaborators here who are working with us to have this project a success in the upcoming 2 years. I would say they are not 2 years around, they are less definitely. We started in June. So thank you for NGCrust, for NFDI, for Chem, for BSTI, for BobChem, for CoFAIR, for CODATA, as well as RDA. All right, so from here, I will move to my next slide, okay, to just, get started in our topic of today of the webinar, what is a chemical? And sounds like a basic questions. However, we are trying here to handle it from the data perspective. We have here experts from different disciplines. We are trying to answer the question, how those disciplines in general are characterize and notate chemical data, how chemical data are applied, so kind of questions like what resources are you using to analyze chemical data, and if you have challenges to manage chemical data, or if you have any lack, we would love to hear about this. And also we would love to hear about your perspective, if possible, about implementation of FAIR data principles and what IUPAC and this project particularly can help you with. And if there is any sustainable consideration, of course, to keep this project going. So we would love to hear about that. So for this, I will love to introduce our moderator, who will go from there to introduce our speakers and start the discussion. Our moderator is Ian Bruno, who is, as I mentioned, very active member in the IUPAC and the CPCDS group. He is also working since many years, about 30 years, in the Cambridge Crystallographic Data Center, the CCDS. And his job as a chemist, since he has a bachelor in chemist, but he has also a PhD in information science technology as well. So he had this combination of data science and chemistry. So his job in his current role since almost 30 years is to develop softwares that could contribute to the development, softwares that help in the science and data activities. The most notable software that he has been working on is the Conquest. In his current role as a director of data initiative, Ian is responsible for establishing strategies that will make the CCDS data more readily discoverable and reusable by wider scientific community. Ian is also, as I mentioned, is very active in other data initiatives, such as this project, for example, and as well as the RDA, the International Union of Crystallographic and International Union, and he's also the secretary of NSHE Trust. Without further ado, Ian Bruno.
Thank you very much, Fatima, for that introduction, not just to myself, but to the project. And thank you also for bringing together all these speakers and organizing this event. I think it is interesting to observe, you've highlighted that it's almost 30 years that I've been at Cambridge Crystallographic Data Centre. And I think my PhD title, were I doing it today, would have been in cheminformatics, but they hadn't invented the term yet. We'd like to start off by thinking about how running a few polls, and the first question for that is to ask you how you identify and to sort of probe to what degree you consider yourself a chemist. So hopefully Stuart is going to launch the first of the polls. And you have a number of choices here. Do you just consider yourself a chemist, or are you specialized in a kind of chemistry related scientist? Hopefully everybody else can see, because I'm seeing the answers, so hopefully everybody else is seeing the ability to answer those questions. Some answers coming in, so yes. And I think there's a number of questions scrolling down here, so asking you about how important machine readability is to your work, then how easy you find that machine readability. And then finally, we'd like to know how aware you are of the FAIR data principles. Maybe you've never heard of them before and this is your first time exposed to them, or maybe you're living and breathing them every day, or maybe somewhere in between. So I'll just give you a few moments just to respond to those poll questions. See, we're inclining towards identifying as chemists here, which is good. And recognition of the importance of machine readability. But yes, and almost not quite an inverse correlation between how important it is versus how easy it is. So it's kind of middling. And an audience who are fairly familiar with the principles. So I don't know if we can keep that. Can we keep that running until such point as you decide to end it, Stuart, or will it get in everybody's way? Yeah. Okay. Cool. And then we'll move on to our speakers. I'd like to express my thanks to them for giving of their time to contribute to this. I think we're lucky to have assembled a group of speakers who span all sorts of different disciplines that have some relationship to chemistry. Our first speaker is Associate Professor Emma Szymanski. She's head of the Environment Cheminformatics Group at the Luxembourg Center for Systems Biomedicine at the University of Luxembourg, so coming to us towards the end of her day. Prior to this, she worked as a consulting environmental engineer in Perth, Australia. Current work combines cheminformatics, computation, and mass spectroscopy. She's been a significant contributor to initiatives that are improving the exchange of data, including the Norman Network and Mass Bank, and looking forward to hearing her perspective on what is a chemical from an environmental science point of view. So Emma, over to you.
Yeah, thank you very much, Ian and Fatima and the rest of you for organizing and giving this opportunity. I've got a lot of slides, so I hope Fatima can, or a lot of animations in my slides, so I hope she can keep up. So I'm delighted to start this off by giving my perspectives on what is a chemical from the environmental sciences perspective. I do have my slides online if people want to download them. I'm also on Twitter. So like I've been introduced, I'm at the Environmental Cheminformatics group, so I was lucky enough to put this term in my group title, at the Luxembourg Center for Systems Biomedicine at the University of Luxembourg. Next slide, please. I can't see it going. All right, so I work with a lot of different people, so I tried to start with where our data starts, and quite often we receive data sets quite like this one, where we have only CAS numbers and names and a whole lot of boxes with interesting metadata for us. This one was at least available in PDF and a Word file. Next animation, please. I should have reduced the animations with the lag. If we're lucky, we sometimes get some images also with these files that we're interested in working on. So this is actually data I've been preparing for a presentation next week, actually. So these are very current examples. Yep, next slide, please. Ideally, we would have, as a lot of us would, our files with a lot of different chemical identifiers. So this is actually a file after we've processed it. You can see here in the light blue, we've got 2 different names describing the chemical. In the dark blue, I've circled some of the identifiers. So we've got PubChem CIDs in there. We've got CAS numbers. And if any of you have worked with Excel and have CASs turning into dates, we've developed also protected CAS number fields so that we can protect those numbers before they're converted. Next animation, please. In the red, you can see the ideal case for us. We've got the INCHI key, and the SMILES as well, so we can recover also the structural information, not just the identifiers. And then in the green, because we do a lot with mass spectrometry, we've got molecular formula and monoisotopic masses, which are really useful data. And ideally, we'll also have the references as well. So this was a super data set of third-hand smoke metabolites, where they actually also put in the PMID and the DOIs of the studies where they got these relationships from. So this is our ideal data set, let's just say. How do we apply this data in our field? We take the substances. You can see there's a drop-down list on the left, the substance name by CAS name or INCHI key. We actually develop interactive interfaces. This is within the Norman network, where you can click the drop-down menu, choose the adduct, and then screen this chemical across, in this case, data from the Black Sea. And you can see, in this case, the distribution of DEET throughout the Black Sea. If you click the next animation, you can see we don't just do this en masse, but we actually have an extraction of the spectral data behind the scenes to also see that the fragmentation data that we have in mass bank matches up with the exact mass, and it's not just a coincidental match. Next slide, please. If we'd want to upscale this is also an example from the Norman network, then we can do this data extraction for many chemicals. So this is a reduced example from REACH. So the REACH legislation in Europe contains tens of thousands to hundreds of thousands of chemicals. And this is looking at the occurrence through different biota, water and sediment samples we have in the Norman network. And you can see, once we upscale this to the different chemicals and the different samples, you can start to see which chemicals are consistently coming in the water, which chemicals are we seeing in the fish, which chemicals are we seeing accumulating in the sediment. So this helps us really gain an understanding of where the different chemicals are landing up in the environment as well. Next slide, please. What resources do we use? I've been doing open science for a long time, so I don't use the CAS registry. I don't have a license for it. I work very closely now with PubChem and other open resources so that we can work together with them to make sure that the information that we use is openly available and accessible to as many people as possible. PubChem has a fantastic interface to a lot of information. Next slide, please. We also work closely with CompTox. So we've had, because they're for the environmental and toxicology, they have a lot of specific data, a smaller data set, obviously. They're under 1 million at this stage, but a lot of the useful information for environmental and toxicological questions. Next slide, please. Obviously, we develop and use a lot within the Norman database system, which is probably less familiar, or a lot of you are less familiar with that than PubChem and CompTox. We have within the database system a large number of databases. MassBank is one of them. Suspect List Exchange that I develop is one of them. And the screenshots you saw before from the digital sample freezing platform is also within this system. Next animation. I just wanted to show a different example. This is now an example. You can see here, of course, you have different isobars for masses. So this is a case where we can extract data for desethyl terbutylazine and simazine at the same time, but you can get a nice picture of them. You can't necessarily tell which of these two chemicals it is at one stage. Next slide, please. Yeah, we also develop a whole lot of resources to analyze the chemical data. So this is the example of Patron, which is an open source mass spectral workflow that actually integrates a lot of different open mass spectral processing tools. So you do the data extraction, the feature finding, processing and prioritization, and then the annotation, which is what we develop. So next slide, please. I'm almost done. What are the challenges we face? They are many. I didn't put any content here because I was hoping we'd do this in the panel discussion. If I would start on this, I'd talk all day. But next slide, please. I just wanted to briefly acknowledge with the next slide, yeah, on my team, I do a huge collaborative work. So it's impossible to put all the names down, but I at least put the photos. I have a fantastic team, a lot of collaborators. Thank you again for the invitation, and I'm looking forward to an interesting panel discussion coming up soon.
Thank you very much, Emma, for that great opening talk. And it's great to see the sort of like chemical substance we deal with sort of put in their geographical locations in that way. If people have questions that occur to them during the talk specifically for speakers, please do add them to the Q&A. We'll probably keep moving through the talks so we get everybody out, and then we'll feed those questions into the discussion at the end. And so our next speaker is Professor Iseult Lynch. She's Deputy Director for the Facility for Environmental Nanomaterials Analysis and Characterization at the University of Birmingham in the UK. She's been involved in a number of interdisciplinary initiatives relating to nano safety, and currently one working on the sustainable future of plastics. She's been taking a leading role, I think, in working out how to adopt INCHI for the reliable identification of nanomaterials. So looking forward to what Iseult you have to say about what is a chemical from a nanochemistry perspective.
Perfect. Thank you very much, Ian, and thank you for the opportunity to be here. So compared to what we've just heard from Emma, in terms of nanomaterials representation, we're still grappling with some big questions. The first of which is a nanomaterial a particle or a chemical? And from the regulatory point of view, it is considered to fall under chemical, but obviously a lot of its properties and its behaviors and its effects are determined by the fact that it has a particulate nature. So that's really what I'm going to touch on for the next little while and explain some of the things we're grappling with. Yeah, so this one, so we started this challenge with the fact that none of the existing databases really cover the complexity of what nanomaterials are. And CAS number, for example, has the same CAS number irrespective of whether we're talking about, a molecular form or a bulk particle, like a large particle, or a nanomaterial. So that was sort of our starting point. And then we're thinking about the fact that when we're describing or trying to represent a nanomaterial, we need to know about its composition. So we do need the chemistry in there. And we will always talk about a nanomaterial based on its chemistry. So we'll say like a carbon nanotube or a cadmium tellurium quantum dot or a graphene sheet or things. So the chemistry always comes first, but inherent in it is the form, the morphology, the size, the shape, all of that needs to be in there too. And then of course, in terms of how we use nanomaterials, we use them as catalysts, we use them as, for sensing, for interaction with biomolecules, and as potentially for nanomedicines. And all of that is dependent on their surface functionalization. So what kind of groups they have at the surface, what they have, and how they're all attached. So at the end of 2020, after a whole year of what I called brain pain, because it really was trying to tease out what's a characteristic, what's a property, what's an intrinsic, what's intrinsic to the material, what depends on the surroundings. We came up with a first proposal for how we might extend the INCHI to cover nanomaterials, and that's the link to the paper there. In the next slide, please, we will see then that we really do need to describe both the surface and the core. You might just click through 3 times, I think, Fatima, just to bring them up rather than having to do it. Yeah. So basically, we also have to think about multi-components, and this is where we had a challenge that we in nanomaterials often talk about the layers of a particle. So we might have a core and a shell and then some functionalization. But of course, in the INCHI, we talk about layers as sort of the features and how we organize the molecules and the bonding layers and things. So we had to sort of think about how we would describe things that come from it being a particle, so surface strain or surface reactivity, things that come from the curvature and things that come from the amount of surface coverage, and then the things that we would be normally used to thinking about in terms of crystals, so the unit cell and the repeat unit of that and the organization of the atoms within it. So all of those need to try and be captured, and it's depending on who you're talking to or the application of the data. Some people might be more interested in the surface properties, some might be more interested in the core properties, but actually we need to know all of them. Next slide, please. So the challenge we also have, though, is that we don't yet have harmonized notation, even in how we describe them. So even for what we call a relatively simple particle, so this is just a silver particle that we're making and functionalizing or stabilizing it with a PEG polymer, a reasonably short chain one, to form this. You might see it called as silver nanoparticle capped by PEG. You might see it AG PEG nanoparticles, PEG AG, with the hyphen, without a hyphen, coated, capping, all sorts of things. No harmonization yet there and how we even name it. Also how we present the size of it, how we present things like whether it's dispersed or not, how we capture the purity, whether there's defects, all of those sorts of things need to be worked out as well. But actually we are making good progress. So with both within the IUPAC INCHI Trust working group on extending the nanomaterials INCHI, we're addressing a lot of these. So there's another publication that's under review at the minute that'll try and tease out some of these things. Next slide, please. So the other thing we found was, in terms of when I mentioned that databases don't work for us, and this is because the very high surface reactivity of nanomaterials means that they are not the same. So the material as you make it is not the same as the material once you disperse it into some medium, not the same as once you put it out into the environment, and so on. So we also need to think about the fact that the characteristics and properties of our nanomaterials are affected by their surroundings, and that leads to these extrinsic properties. So we need a database that can link what we intended to make, so the synthetic material that we made, but then that can link to how it changes during storage, how it changes once we disperse it, and how it changes throughout the lifetime of the experiment even. Next slide then shows how we're beginning to tackle this. So we've thought about the concept of the instance of a nanomaterial. So each of these blue boxes represents something that we're doing to our nanomaterial and the set of characterization data that we would need about it to tell us what it is. And our database structures then need to have that link between the parent and the transformed instances of our nanomaterial. And when we have these instance maps, as we call them, we can then tease those out to develop the data capture templates and the representation of the forms, and therefore then a more harmonized way to sort our data. Next slide, please. Our goal with all of this is to develop a platform that is as well established for nanomaterials as Unichem, for example, is for ordinary chemicals. And we're doing that mostly, I think, at the minute through the KNIME nodes, but we also do have colleagues now who have been developing Python codes and things as well to help us with a lot of this. So at the minute, we have an alpha version of the NINCHI, or the nanomaterials INCHI, and we have a fairly simple web app that can build it. What I should have said, of course, is that we have to stay within the INCHI universe. So we have to, for the ligands and the small chemicals, we're continuing to use the INCHI for that ligand as it already exists, and then we would tag it to the nano piece. We're also working very closely with people with the reaction inchy and the mixtures inchy to make sure that it all fits in together. And how it's used then will depend. It will, you know, a lot of the drive for doing this is for nanoinformatics, so that we can develop predictive models of how particles will behave and how, whether they're toxic or not, but also a lot about this nanoform. So there's quite a regulatory push as well to be able to distinguish one nanomaterial from another. Next slide, please. I think that might be the last one. Yes, the challenges. So there's a lot. But it's super exciting. And I think, you know, as part of WorldFAIR and building on what the chemicals space is doing, there's a lot we can learn. We do have databases that are really emerging and developing fast. The instance maps and the linked data capture templates will be huge. A huge step forward. And of course, we have to balance between doing everything that we can versus being a bit pragmatic and just getting solutions that work. And as I said, we're at the stage now where we're, you know, beginning to develop the web apps, the APIs, the NIME nodes, and all the things to help us do this, but it's still a long road to go. And of course, the projects and the people. I'm impressed with Emma's slide. I must try and develop something similar that really just shows how many people are involved in all of this. It's endless. And thank you for listening.
Thank you very much, Isel. It's fascinating just to see the challenges of sort of like, yeah, the kind of like, yeah, the characterization of these nanoparticles and particularly that transformation piece about what you start with and then how it transforms when it moves into the environment. So yeah, that you've highlighted some very real challenges there. We're very, very grateful to our next speaker, Leslie Wyborn. She is joining us from Australia, where I believe it is about 2:32 in the morning, which I think is above and beyond the cause, but we're really grateful to have her coming along to give us a perspective from the geochemistry area. Leslie is an honorary professor at School of Earth Sciences, Research School of Earth Sciences, and also works with the Australian Research Data Commons. She has prolific involvement in Research Data Alliance and CODATA activities who are sponsoring this WorldFAIR project. And she's always encouraged and engaged in chemistry related activities taking place in these venues as well. So with over 4 decades of experience in mineral systems, geochemistry and geoscience, looking forward to Leslie bringing us down to earth and telling us about what is a chemical from a geochemistry perspective. Leslie, over to you.
Okay, if you've got my slides, right, okay. So this is presented for and on behalf of a group of us who've informally come together from Australia, Europe and the US to form a group called One Geochemistry. Next slide, please. And so what I'm going to do in my talk is give a very high level view of the chemistry, and then Kirsten in her next talk will drop down to that more detailed perspective of just one field of geochemistry. And geochemistry is just fundamental to understanding past, present and future processes in natural earth systems, including the evolution of the earth. And it's societally relevant to many domains, including environment, resources, minerals, energy, etc. So I think disadvantages, it's just too prolific. Next. So I just thought I'd say, what are our challenges? And our challenges are not really technical, they're social. We just, in this field, even though it's been going since 1838, there's limited history of sharing data. It ranges, it's very heterogeneous. It ranges from simple, cheap elemental analysis to complex isotopes. And I often joke about how a lifetime collection can fit on a 2 gig thumb drive and transferred as an email attachment or word of mouth, as it's called. Despite this long history, we've got no agreed community mechanisms to develop, promulgate and store standards. And there's very limited understanding that FAIR means machine actionable. We don't have a single science union for geochemistry. There are multiple societies and associations across the science unions. Very few have standards working group. Skills and training are bad. As I said, we have many excellent researchers, but few data scientists to understand how to structure data and few understand the need of the consistency of terms, even the spelling of attribute names, particularly in machine to machine. And so what's lacking or inadequate standards, vocabularies, ontologies, etc. Next, please. So again, we always say that you've got three components, and it's a bit like Isolde just said about she has different environments. We have multiple different samples on which we put analytical science and different chemistry techniques. And so you've got your analysis, your raw data, unknown calibrations, secondary materials, multiple ways of data reduction, chemical concentration ratio, and you've got multiple analytes, ratios and methods to analyze these. And so we sort of at, you'd like to say, the starting point of zero, and I do try and not say we're at ground zero. Next. And so this is a little bit complicated. I just wanted to say we've to try and, what can I say, streamline and accelerate how we're trying to develop standards. We're looking at this W3C OGC sensor observation, sampling, actuation, ontology, and we'll simplify it in the next slide, please. And you can sort, no, back one, please. And you can sort of see how we're saying, well, if we use ISO time or units of measure, or how you describe the location of a specimen or the instrument that we used, they're common to science. And then we started to listen to Ian and others talking about what's going on in chemistry. And we thought, well, hang on, you guys have got a lot of stuff with the IUPAC color books. You've got chemical vocabularies in IUPAC over here in the right, and you've started to formalize how you've got your methods. And so the differentiator then becomes within National Unit of Geological Sciences and things like MINDAT, we actually have standardized ways of how to describe a standard. And so what we're trying to do now is get the community together to say, well, what do you need? What is it you want? But see where we can leverage. And that's why we're trying to just get together with the IUPAC group and see what we can learn from you. And it's not just the standards that you've produced, it's the way in which you've developed and promulgated those standards and published them. There's a lot of key learnings we think we can leverage from that. Next. And so now we come to WorldFAIR, and as I joke, chemistry, nanomaterials, and geochemistry are in the red hot theme with chemistry and nanomaterials. It's very clear we need to leverage IUPAC standards as well as their standards government structures. But I was talking to a colleague against Clump the other day and said, well, hang on, we haven't even thought of INCHI. And so what we have in a lot of our chemistry and geochemistry work is we have things like IGSN and MINDAT for identifying each instance of a sample or a mineral specimen that we identify. And we ask the question whether or not we could look into using INCHI for substances, mineral compositions, isotopic ratios, but we need to consider that a substance of the same chemical composition can have multiple mineral structures, and one mineral structure can be a solid solution. And we're really hopeful that you guys have solved that so that we can share that with you. So that's just an oversight of the theme geochemistry at a very, very high level. And Kirsten will show you how we deal with it within one specific domain. Thank you.
That's brilliant. Thank you very much, Leslie, for that overview. And as you remarked, the sort of parallels there with some of the nanochemistry challenges are interesting. And I think I'm glad you highlighted IGSN because it links quite nicely to our next speaker, who's been one of the driving forces behind IGSN, which for those who don't know is an international identifier for samples. And I think that it's quite interesting to think about the complementarity between that and INCHI. And I think there's probably some really interesting conversations to be had there. But Kirsten Leonard is our next speaker. She's based at Columbia University, but plays a leading role in a wide range of earth science initiatives, including AIDA, CSAR, EarthChem, and the Astromaterials data system, which I think we're going to hear about shortly. And so, yeah, I think you're going to talk to us about cosmochemistry and what a chemical means out in space. So over to you, Kirsten.
Yeah. Thanks, Ian, and yeah, thanks for including us in this. I mean, this is a really great example of how we can work across domains to learn from each other and converge on standards. So can I have the next slide? So yeah, I chose a field that is actually new for me as well in dealing with data management for astromaterials. And I wanted to give you some insights into a very specific example of astromaterial science. Next slide, please. Just to start off is what is, the study of astromaterials is very often referred to as cosmochemistry, as a parallel or maybe a subdivision of geochemistry. It is really using chemical analyses of extraterrestrial materials to understand the evolution and processes in the solar system and actually beyond. It's primarily laboratory analyses, but there is also a substantial branch of using instruments in space for spectral analysis of materials, of planets, and so on, to identify chemical compositions. But what I'm talking about, can you click again to bring an animation in here, is sort of giving you a feeling of what I'm talking about with astromaterials. Primarily, we have large collections of meteorites all over the world, which are extraterrestrial materials, but this is actually the set of sample collections that the Johnson Space Center of NASA is managing, which has a large collection of lunar rocks. Those are all the ones brought back by the Apollo spaceships. But then other collections include cosmic dust, solar wind, and now an increasing number of samples from asteroids. And that's what I'm going to be talking about. Next slide, please. Well, let me step back first in a more broader overview of cosmochemical studies, just to give you a feeling of what it's used for. So, for example, all these Apollo samples have been analyzed painstakingly and have driven a huge evolution of analytical chemistry, analytical instrumentation to study these samples. And they have been compared, for example, with rocks from Earth, and it has been found one of the outcomes is that the lunar samples were depleted in water and sodium and other volatile elements, but they have identical oxygen isotopes to Earth, and that has led to this theory of the moon being generated by an early solar system collision between the Earth and a Mars-sized body. Meteorites, studies have, for example, shown that some of these meteorites were different. They had very young ages, as was determined by radiogenic isotope ratios, and they have been found to contain gases that have compositions identical to the Martian atmosphere, and so they have been identified as pieces of Mars. Other isotopic anomalies have been found in meteorites that have led to the discovery of tiny pre-solar grains that I actually showed on the intro slide, and have led to finding out about many different kinds of nucleosynthesis inside of stars. Next slide, please. So what is currently happening is at NASA is a mission called OSIRIS-REx. You might have heard about it. It's a spacecraft that went to collect samples on the asteroid Bennu and is currently on its way back to Earth with a great set of material that was collected. And there is a worldwide team waiting to analyze these samples. And in preparation of these analyses, the group that is running the data management has been trying to identify standards for all these measurements. And over 60 different data types have been identified that have been categorized here into spectral analyses, mineralogy, petrology, elemental and isotopic analyses, organic analyses, and physical and thermal properties. Next slide, please. This is just to show you, the diversity of measurements that will be done. And if you click again, I've kind of enlarged some of the words here to be more readable. So there is the whole bulk elemental abundances. It's going to be measuring basically the periodic table of elements in these samples. Noble gases, isotope ratios of oxygen, of nitrogen, all the noble gases anyway, that's important. The same for hydrogen, carbon, and so on. And then lots of different isotope systems in metals and in all kinds of other elements that have a meaning. Next slide, please. This, what they've also identified already is the range of analytical techniques that will be used to analyze all these. And I've just copied one list here that was identified for elements and isotopes, the category, which is a huge list of different measurements, and they all need specific reporting standards and formatting. And this list is clearly not final. It will keep evolving as researchers will optimize technologies, analytical methods in order to improve precision and basically get the most information, the most scientific knowledge out of these samples. Next slide, which I think is the last. So from the perspective of a program such as OSIRIS-REx, there are clearly many challenges, and that is, as I just mentioned, this constantly evolving set of analytical methods. There will be new chemicals that will be added to the list of measurements that need to be done as they are found to provide new information. We do measure chemicals in many different components. This is something that Leslie already mentioned. There are these pre-solar grains, tiny nanoparticles actually within the samples that need to be analyzed and are different. And again, what was a big hindrance for the program is that there are no discipline-wide data standards that could just be adopted. Rather, the program had to develop their own standards. It's difficult to capture with this range of analytical methods to capture all the workflows and all the calibrations and the data reduction from raw data to model data. People use different types of normalizations to report the data. So there is the danger of having inconsistent reporting. And it's also a big challenge in these samples to analyze different components of the samples with the structural context, the actual surrounding of a given component in a sample. And that leads to new technologies of capturing the spatial framework of individual measurements done in situ in these samples. So this is just giving you a bit of a real world example. Thanks. That's it, I think.
Thank you very much, and I think it's as a real world example. I think it just highlights the complexity of what's out there. I kind of feel if we can, capture it for this use case, we've probably solved the problem for all of chemistry.
Yeah, right.
It feels like it's a whole ecosystem where every challenge is represented. So that was fascinating and challenging, but also inspiring, I think. So thank you very much. Next speaker, we're staying in outer space a bit actually, is Dr. Marie-Lise Dubonnet, a lecturer at PSL University and a researcher at the Observatoire de Paris. She's led a number of large European infrastructure projects and been a director of laboratories and institutes, but is also founding chair of the Virtual Atomic and Molecular Data Center, VAMDC. This is providing interoperable infrastructure for connecting various resources to do with atomic and molecular databases, and looking forward to hearing about her experiences handling chemicals in that context. So Marie-Lise, over to you.
You can start.
Adam, we're not hearing the audio.
Can you hear the audio or no?
No.
Not at the moment, no.
So I'm going to talk about
Sorry.
Now, yes.
Okay, let me try from the beginning. Okay, let me know if you cannot hear it. Okay, because if you hear it, I think if you start talking, I think it's going to be stopped. So
chemistry in astrophysics, focusing on atoms and molecules. So a large variety of atomic and molecular data are used in astrophysics and other fields for the analysis of spectra and of properties and for the development of models. Many resources have been created over time, many databases that contain spectroscopic data and data for other microscopic processes, many astrophysical data analysis software and modelization software that include usage of laboratory atomic and molecular data available. And efforts have been made concerning the interoperability of databases through different initiatives, and I'm going to talk about the Virtual Atomic and Molecular Data Center. And further standards have been developed with CODATA, IUPAC, NIST, IEA. So the life cycle of atomic and molecular data starts with the needs, and in that particular case, in the needs in astrophysics, where they observe images and spectra which are analyzed, and the results of the analysis are compared to the results of the modelization of objects such as the interstellar medium, the sun, and both involve atomic and molecular processes, so atomic and molecular data. Therefore, we deal with issues linked to easy access to the data, traceability of the data, for example, citation of the data. And these issues and more issues have been addressed by the Virtual Atomic and Molecular Data Center, which has been created in 2009, and it created a full ecosystem that gives an interoperable access to roughly 41 heterogeneous atomic and molecular databases. And this ecosystem has been all the processes and all the vocabularies for finding the resources, for querying the data, for retrieving the data and transforming the data have been standardized. And the species we are dealing with are molecules, atoms, can be very complex structure. To describe and annotate the data and to transform them, we design an XML schema for atoms, molecules, and solids. And this is a collaboration that started with NIST and IEA. And for atoms, molecules, we describe them at the level of quantum chemistry. We describe the processes involved, where those particles and atoms and molecules are involved, processes that occur in the interstellar, in the astrophysics, atmospheric physics, and so on. And as well, we attach rich metadata to those data with provenance in the data sources methodology. We design as well dictionaries, which are based on the vocabulary used in the XAM schema. And this is used to query the infrastructures. From all the standards, we design tools to handle this data. For example, the portal that find, access, retrieve interoperable resources across databases to be reused, the spec code tool that takes advantage of interoperability of quantum numbers, and then it can cross-match heterogeneous databases such as spectroscopic information and collisional data. The species database that we design allows interoperability on the species ID throughout all the databases, and one part among the vocabulary is included the INCHI key. And finally, the query store stores all the queries and allows reproducibility and traceability because it assigns a unique identifier on queries and GOI through Zenodo. So what are the challenges in the FAIR implementation? The first thing we analyze is that we are lacking machine actionable metadata for the registries, the species database, the query stores. It's internal to the MDC, but it can be used in cross-disciplinary access. And we perform this analysis using the FAIR data maturity model of the Research Data Alliance. And then we believe that we are missing, and it would be useful to have machine actionable vocabularies that for example, in the processes, in the description of the atoms, states of the atoms, in the description of the species for molecules, in the description of the queries, and as well in the description of the quantum numbers for molecules. So what do we expect in the collaboration with IUPAC? General goals: bring our standards to IUPAC and interact to see how that could be useful to IUPAC. To flow the IUPAC work on the WorldFAIR project so as to orientate our future developments accordingly. And as specific examples, in link with machine actionable metadata and vocabularies for fairness, examples would be identification of species, identification of states, identification of reactions. And what are the objectives? The objectives is that other communities adopt those metadata vocabularies, and such as astrophysics, atmospheric physics, and plasma physics, data communities use atomic and molecular data. Thank you for your attention.
Thank you very much, Mary-Lise. I think thank you as well for reminding me, certainly, and probably some of us, about the quantum level of describing chemicals as well. I think for me, it's stuck in that sort of simplistic atom and bond model, but yeah, actually these chemicals are so much more complex than that. And congratulations on what you've achieved so far with the AMDC. You mentioned physics there. We're sticking a bit with physics because next we have Ken Cronlin, who's a scientific data architect at Citrine Informatics, but has almost a decade of experience at NIST before that. Background in multi-physics modeling, good software engineering and data transformation, and now working to understand how good representation of data and data-driven methodologies can help lead to better materials and chemicals. So Ken, over to you to give us your take on what is a chemical.
Thank you very much, Ian. So I'm going to be coming at this from an industrial perspective this morning. Obviously, I used to be much more involved with the research community side when I was back at NIST. First slide, if you please, Fatima. And we can actually go to the next one. But we're really talking about the question of how do you engage with people who aren't sort of up to date with this and whose data will never be open, though obviously we can work with them to help make their data fair. Material science, 100 years ago, it would have been called metallurgy or mineralogy or ceramics engineering, depending upon the department. But, you know, it's this hodgepodge of all these different methodologies to try and accomplish a particular goal. It really is sort of the start of interdisciplinarity in terms of research. And so it's a blending of chemistry and physics and engineering. And ultimately, it's this careful and repeatable arrangement of atoms that we care about. And so that means that the line of what is a chemical and what is not is very ambiguous. Materials data is ridiculously small, it's sparse, it's heterogeneous. You're always trying to predict very far away from a whole bunch of previous experiments, and all your experiments are clustered in this really high dimensional phase space. And every single new experiment is expensive. So it really is, what resources can I find, and what do I need to, and what can I sort of mash together in this hodgepodge in order to make a functional model for predicting what my next step can be. Things like classic design of experiments is just too expensive. And so what are the materials discovery challenges? First, very small changes result in massive physical variation. And so you really do need to think about this as sort of local approximation, local expansions, rather than trying to fit global models to these things. And the space of possible solutions is very, very large. Continuous values are pretty easy to optimize, but usually you're dealing with a combinatorial issue of trying to develop a formulation, an ingredient list with amounts. And that is just a massive space on its own. And we also want to take a look at, we want to be able to predict for novel compounds that have never been measured. And that's really the trick here, right? That's getting much more into like the pharmaceutical attitude towards cheminformatics, where you're trying to deal with things you've never sort of looked at before. You don't actually have properties for these things, but you still need to predict performance to figure out whether or not you want to pursue this. And so it requires a huge amount of expertise, many diverse, very diverse data. And again, so it really is just like data engineering in terms of combining all this stuff together in a variety of resources. Slide, please. And so I'll go through these very quickly, play this back at quarter speed if you want to actually read the content. As Isolde pointed out earlier, materials have this chronology. She was talking in terms of nanomaterials. We call this material history instead of an instance map. But you have to keep track of all the different things, all the different environments that this material experienced over the course of its evolution to actually understand the final product. Next slide, please. We also have to deal with helping an institution that's never worked with the idea of an ontology or a controlled vocabulary to take the jargon that they've used internally and map that onto controlled vocabularies, and then aid them with the crosswalk with existing schemas, because you can't just force them to use an external vocabulary, because oftentimes the vocabularies that they use are sort of fractally nested. You don't use the same terminology with polymers as you do with alloys. And when you're talking about steels versus aluminum alloys, those are completely different terminologies as well. So it very much is this deep dive where you don't, again, you don't even have this global data concept model. You're not even ignoring the concept of a physical model that you can translate. Slide, please. And so the most essential thing is you have to be able to handle this range of identifiers. You need to be able to link into these historical databases, chemical safety databases to pull in a lot of the toxicity information. You have to be able to link into purchasing databases so they can understand how that relates to their inventory. You have to link into resources like PubChem. I remember a time before PubChem, and the collection of that information is fantastic, but it's still, we're oftentimes going out into these dark corners that haven't gotten vetted, and so there's a lot of complexity. And so it really is, we need to be able to create knowledge maps. Knowledge maps are absolutely essential to creating this sort of synthetic, very, very one-off sort of set of interrelationships you need to solve today's problem. Next slide, please. So we create graphical models. Essentially, each one of the little submodels, each one of the boxes here is its own AI trained system, where we essentially have a flow of information through our system. We have to be able to impute places where data is sparse, so we can sort of start making educated guesses and slowly accumulate information, have people do experiments to sort of fill out this tree and online update of this information in order to actually get a final model that's going to lead us eventually towards a better product. We're not talking about, a one shot, we're going to tell you the solution with one model. We're talking about, we're going to cut the number of experiments you have to run in half. That's the kind of goal we're talking about. Replacing classic design of experiments where it'd be impossible to do all this stuff. And in particular note, with regards to chemical featurizers, we're oftentimes dealing with maybe a name and maybe a CAS number that we need to map to a SMILES, and in organic space, we're usually dealing with like a chemical formula, an empirical chemical formula, maybe something like a structural if we are lucky. Again, that maps very much tightly to what Emma and Isolde were talking about at the beginning of this conversation. We use a Markov chain Monte Carlo to try and explore this incredibly high dimensional space, but it really does get into a place where it's very hard to talk about. It's pretty easy to optimize a one-dimensional real number or even a high-dimensional real number, but doing the kinds of moves that are talking about swapping ingredients in and out and figuring out are ingredients comparable and how can you do that in an efficient way, because exploring space of this magnitude, of this dimensionality, is just deeply expensive from a computational perspective. Next slide, if you please. So how can we explore chemical space? We can get into this a lot more in a minute, but when you get to the panel, but chemical spaces are really, really challenging because they don't map to this to sort of classic mathematical approaches. Oftentimes we're dealing with either combinatorial recombination of fragmented molecules, or we've used stone selfies and generative models in order to try to come up with new molecules that might be of interest. But again, the complexity explodes very quickly and explodes in the technically correct sense, in a factorial growth in terms of search space size. And then last slide. So what are the challenges we're dealing with? First off, we're coming and meeting scientists, material scientists at companies who have very little expertise here. And so we're essentially doing ground, education first and foremost. And this is very hard and this is very expensive. And so making the tools more accessible to less computationally sophisticated folks is really going to be key in terms of making this much more applicable and useful for them. We spend a lot of time building the software, building the tools to try and make that helpful. And then we always need high quality data resources. And with, uncertainty would be magical, because everything we do, because of this small data issue, we propagate uncertainties through these graphs so we can actually talk about likelihoods of improvement, probabilities improvements, because we're playing a numbers game rather than actually, again, giving these discrete hard predictions. So hopefully this bit of industrial insight is helpful, and I hope I've stayed within my 5-minute allotment.
Thank you very much, Ken. And I think, again, something I see emerging now in some of these recent talks is that importance of, it's not just about the atoms and the bonds and how they join together, but describing those concepts. But I think what you've brought in there is the relationships between those concepts and how quickly that can sort of become both an opportunity, but also a challenge to try and encapsulate. And no one person describes things in quite the same way as the next person. And how do you deal with that challenge as well? So thank you for that insight. Now, finally, we were due to have Professor Brad Olson from MIT join us, but due to an unexpected change of circumstances, he wasn't. But we are incredibly grateful that Dr. Dylan Walsh, a postdoctoral researcher working with Brad, has agreed to take his place. Dylan's research is focused on the development of intelligent automated reactors for polymer synthesis, and he's also a core developer of community-driven data and informatics ecosystem for soft materials known as CRIPT. And he's going to give us this perspective on what is a chemical from a polymer science point of view. So Dylan, thank you, and over to you.
Yeah, thank you. All right. So on my first slide, yeah, I'm here representing CRIPT. It's the community. Ooh, can we go back one slide? Yeah. Community resource for innovation in polymer technology. The mission of kind of this organization is to provide an open source polymer data ecosystem. This project is a collaboration between MIT, University of Chicago, Citrine, Dow, and NIST. We're trying to bring together both academic, industrial, as well as national lab kind of motivations to kind of bring together a whole data ecosystem for polymer materials. Okay, first slide. Yeah, so polymers, they have a wide range of commercial applications, from 3D printing to tires to packaging. How we think about characterizing and notating them is one of the main things we think about in this field. And I think it really starts with the name polymer, which means poly is many and mer is units. And this is one of the things that we really need to deal with right off the bat. So if we look at here is our line notation, we use a very similar one as you would see with small molecules, except we add in these parentheses. These in parentheses kind of try to emphasize this idea of many units. And really, we talk about this in terms of stochasticity. And when we really think about polymers, we have many layers of stochasticity. So we have it in not only the chain lengths, but compositions and topologies. And we think of them about sets of structures or ensembles of structures. And this is really one of the big challenges in this area is how do we represent multiple layers of stochasticity so that a computer can understand it, or that we can think about representing it for database searching and these kind of things. We're not dealing with single values, we're dealing with distributions and distributions on distributions that we need to kind of think about representing just to explain to the computer what we have and what we're trying to discuss about. Next slide. One of the big things in this area is how we use it. I think one of the maybe overstated things is our daily research. We use Google a lot just on our day-to-day things, whether it's figuring out how to make a material, looking up boiling points, melting points. I'm on Wikipedia quite frequently for small molecule stuff just to get like simple data. And for polymers, it's the same thing. I want to look up the solubility of something. This is something I do on a daily basis, multiple times a day, and that's really a valuable use of data. The second, and maybe the more exciting one, is obviously the machine learning data science, where we'd like to, take some data, make a model, and then, find some new sustainable plastic with the desired properties that we want for our new applications. And that's a really exciting thing, but that's definitely something that we're not there yet. But the daily research thing is something I think we're trying to address maybe a little bit more immediately in this context. Next slide. One of the things that I think we want to discuss is probably the challenges for sure. And kind of what I alluded to, and I think I've seen it in some of the other talks today, is representation is a really big thing. How do you even describe the material that you're trying to make a data structure about? And I kind of alluded to the stochasticity as one of the big things that we have to deal with in this area. Some of our technologies that we've kind of worked in with the crypt stuff is things like big smiles that try to extend smiles to handle just at least providing that notion that we have stochasticity. And then we've worked on now adding the quantification of that stochasticity. But polymers also, as I've seen with some of the nanoparticle stuff, form these kind of assemblies. And that's important when we start thinking about attributing material properties to some sort of polymer, is you need to know what assemblies, and you actually even need to know what processing happened to actually attribute that property to something very specific, because processing and these assemblies change those properties. Accessibility in our field is a really big thing. Most of our literature is tied up in publications, and reading hundreds of publications is infeasible to find the information you're looking for. And I would kind of argue this, and this might be somewhat controversial, but we don't know what we do in our, or what has historically been done in our community, because it's just too time consuming to go and read hundreds and hundreds and hundreds of publications, what has been done before. And I think that challenges what problems we think about in the future, because if we don't know what we've done before, how do we know that the solution that we're looking for isn't already done and we just need to find it? And that's where I think bringing accessibility is a big thing. And kind of along that is findability and searching. So if we can't represent these materials, how are we going to search these materials? And if we can't even do things like, draw a chemical structure, how are we going to find the information or data that we want? And this goes along with even, I think about like filtering. If you're going to do machine learning, how do you filter down to the data sets that you want if you can't represent the material to do that filtering? And that's one of the big challenges, or these are a lot of the challenges that we think about in the CRYPT organization. And as we think about kind of putting together a new database, a new data infrastructure kind of for polymer materials. Thank you.
Thank you very much for that wonderful summary of the challenges in your particular area. And I think also for just grounding us in that reality of the day-to-day is, where do people go when they want to get information? It's Google. And I think, we obviously need to sort out these representation issues and challenges, but we then need to think about how do we embed them into people's everyday workflows. So thank you for that insight. That's great. Right, we were hoping to have about 30 minutes at least for a panel discussion. We have about 15 minutes at that. And in this 15 minutes, we're going to tackle vision for implementing FAIR, sustainability of it all, and how IUPAC can collaborate. Now, I think that's probably far too big an ask for 15 minutes. So I think I'm going to cycle through the panelists, and I'll do it in the order in which people spoke, which means Emma, you'll probably you're going to get this first, so feel free to just observe whatever you want. But I think what I'd ask people to think about is to identify one or two common challenges that you feel has come through, that you kind of look at your own sort of area of practice and hearing about others that you think has really come through. Reflect on maybe what the biggest challenges might be, and in particular where IUPAC as the International Union for Pure and Applied Chemistry might most be able to help. And you have about 1 and a bit minutes each. Emma, if you're
Well, I'll
happy
be
to
quick
start.
then and say I think the last point was also good. I mean, people need to be able to search and find their information very quickly, and this is where established identifiers, we use Inchi keys all the time. Not being able to do this for polymers, and not being able to have a standardized extended smiles to be able to represent the polymers correctly, because we also see these signals with these mixtures in our samples. And the UVCVs are the biggest challenge for us at the moment. We know we have technical mixtures that we can't search. Isolt also showed it quite well with the nanomaterials. These are all out there in the environment. All the data set I showed with the discrete chemicals, but it's these having these identifiers for these challenging mixtures to search and exchange information on those would be fabulous. And I think this is also where IUPAC can help, and has helped a lot in the past, and can hopefully help in the future.
Brilliant. Thank you very much. Isolt, from your perspective.
Yeah. So I would echo what Emma said, and I think for me, one of the things that I think came through quite clearly from the polymers, from the materials design, and also from some of the geo and cosmic materials, there are, I mean, these materials are very heterogeneous in their nature. So, and we've been thinking a bit about, for example, using, distributions, and I saw distributions in terms of polymer chain length, distributions in terms of phases and things like that. So how we can capture, and how we can capture some of those sorts of distributions, and not think of things as being static. And I think also, even just coming back to Emma's data, which was, she showed really nicely in the fish, the water and the sediment, I think we think about, I think mercury, I think, is a really good example that I use in my own teaching as well. That it has inorganic and organic forms, so like methyl mercury, and sort of being able to think about and distinguishing those as well, because they're not the same and they behave very differently, and they have very different toxic effects and things. So yeah, I think IUPAC will have, I think the fact that we're having this conversation, and the fact that we have a project now that works across these different domains, is wonderful, I think, because we already from this session I've learned so much, and I've several ideas of things that we can connect on and develop together.
Thank you. Leslie.
I think this has been really great, but what I'm arguing, because domains, is that this is what we call the long tail community, where it's small, it's heterogeneous, and it's an absolute pain to sort it out. You don't have these kinds of problems with the big data sets in say geophysics, climate, etc. But I think the other thing I'd like to say, I noticed all of you were hinting a little bit at FAIR, and making the researchers understand what FAIR means, what machine readable means, and whether or not we can start to get together through IUPAC or WorldFAIR to actually say, listen, there's no point in the informatics people going right down the path and solving everything if your audience doesn't understand what machine readable or vocabulary, etc. is.
Important piece about education and culture, I think, is kind of, comes to the fore there. So I think, Kirsten, what would you add to that?
Yeah, I fully support what Leslie just said. But what stuck with me was actually something that Ken referred to. It's the modularity of things. This whole landscape is incredibly complex, and with lots of different challenges and facets of chemicals. And I think it's really important to identify what the core commonalities are, and that's, I think, where IUPAC can contribute, and be it, just defining chemicals, representations, and so on, and building a coordinated structure where these modules can serve, the more specific aspects of the chemistry landscape, be they in the environment or in space, and kind of offer this to the whole community, so you can kind of mix and match as what you need. That would be sort of a vision that I take away from this discussion.
Thank you. Marie-Lise.
Well, I was very interested to listen to this webinar. Thank you very much for inviting me. Listening to you, I found that finally we spent not 20 years, but nearly doing very simple things to reach the present state of VMDC. So I wish you good luck because we haven't solved everything since I'm here. And I will repeat, what we would like to have is to have some high-level control vocabulary and possibly machine actionable vocabulary, so that the fields which use atomic and molecular data and the data from the infrastructures that collect, that coordinate all those data, they use the same kind of standards and they do not reinvent the wheel, which is currently what is going on. Each application field using those data, they want to do their own little data model and blah, blah, blah. And that's going to be a nightmare. So I think things should be taken at the highest level through CODATA, IUPAC, and this kind of project, RDA, and so that we can make decisions, and then everybody will apply those decisions. Even VMDC will adapt in time. We have 41 databases, so it's a lot of databases which are very different, and it will take time to implement the decisions. But first, we should have decisions on many aspects of vocabularies and machine actionable vocabularies. That's why I contacted you.
That's great, thank you. And I wonder if there's a sort of education piece there about getting to PIs as well, because what you say about people do like to come up with their own solutions to problems.
Yeah, but you know, everybody, we must understand that when I talk about the kind of data I'm talking in VMDC, our users are both our own community, atomic physics, molecular physics, but there are as well the other communities, which might not be your case when you spoke. My user are Astrophysics, and they have already their own infrastructure and standards and interoperability. Another is plasma physics. I looked around the world, plasma physics, it's not much going on. In the UK, I found a postdoc position, for example, for fairness in relation to plasmas. And there is an initiative in Germany as well, a small initiative. And atmospheric physics, for example, they might consider doing as well their own standards. And so there is a need for coordination so that people do not spend time reinventing the wheel and inventing even vocabularies, you know, because nothing is interoperable. So that I think that IUPAC has a really a key role to play here, so, and in that field.
Thank you, Ken.
Thank you, Ian. First off, yeah, fantastic panel. Thank you all for including me. First, I think the most important thing we can do to have a high impact is the cookbooks work. I'm super excited that I'm participating in that. I encourage everyone else to, because I think that that's rising the tide for everybody. We have a lot of people who are like motivated to do this stuff, but inexperienced and are, you know, they're going to have difficulty. 99% of quasi-structured data in the world lives in Excel workbooks. And those of us on the computational side should never forget that. That's the community that you need to reach out to, because that's how you're going to crowdsource good structured information. And I keep harping back to computer programming, software engineering, because they actually have some really good ideas they've developed around interoperability and reliability in systems. And, you know, for example, Marie made reference to people constantly inventing their own things. Not invented here is a very common trope within the software engineering community. So taking a look how we can bootstrap in some of those good forms of practice into software scientific methodologies here, I think can be hugely valuable. And having good cookbooks out there so that people can get out there and start seeing what a controlled vocabulary can buy them will get them to really start buying in emotionally with working with these sort of larger systems, getting into an actual interoperable state. You know, the I in FAIR is always where everything falls apart, right? And then the last thing, I just wanted to make a quick comment that I think I saw this sort of spread throughout, that the idea of a chemical identifier is kind of an emergent thing. It sort of depends upon like the context you're trying to work it with it, like whether or not you're worried about things like weathering, whether or not you're worried about things like, is this a disconnected structure? Does it need to represent both inorganics or organics and crystal structure? And so trying to represent something that's an emergent overlap of multiple concepts at the same time as it's computationally distinct is something that I've chewed on for a very long time and I don't know a solution to. But if IUPAC wants to like throw its weight behind that and try to understand how do you communicate the diversity of identification in something that's computationally actionable, that would be that's world changing.
Thank you for that. It's a very valid point, and I think that came through to me with all the sort of different, particularly as you get into the inorganic sphere, about how, yeah, we are lacking those standard ways of being able to represent those sorts of things. So, thanks. And finally, then, Dylan, your thoughts?
Yeah, I really like a lot of I think what Ken was saying, especially around the idea of interoperability. You know, I think we all probably fear that there's going to be, 30 databases all in the same area doing different things with different needs. And to some extent, I think, at least in our experience, we kind of accepted that. And one of the things we've definitely focused on is interoperability. Handing out like, these are key identifiers or key things that we need for your database to be, interoperable with ours. Maybe you can include them in your database and we can include yours and ours. And that's how we can grow as a community with multiple different databases. That's one of the approaches we've taken. And so maybe IUPAC can think about how to maybe facilitate that interoperability and bridging across different representations. Because I think some cases, they do need different representations than other people do. And creating a completely universal thing for everything, I'm not sure if that's an achievable thing. I mean, it would be ideal if we could, but I think that's a hard task.
Brilliant. I think that's a great thought to kind of end on there. And I think, again, it reflects that pragmatism, right? There's only so far that you're going to be able to get people to do exactly what you want to do. And so how do we constructively manage that diversity of creativity that exists across the chemical sciences and all the disciplines we've heard about today? So I will just add my thanks once more to the speakers and hand back to Fatima to wrap this up.
Thank you, Ian. Thank you, everyone, for this great opportunity and for the great talks and the discussion, and bringing that coordination, how coordination among the disciplines is important, as well as our IUPAC can help with. I just want to have like a few minutes to go over a few announcements, and perhaps before the announcement, we could start, Stuart, if you wouldn't mind, launching a feedback poll that we would love to hear back from you about what you think about this particular event and how we can, what we can bring in, and then our next and upcoming occasions, similar occasions.
Polymer is launched.
Yeah. Can anybody see the okay,
Yeah,
I can see some answers right now. Okay, perfect.
Stuart, while people are filling that out, can you show the results from the other poll, or will that confuse the system?
Let me see if I can show the results of one while I cannot, unfortunately. While we're doing this poll, I can't show the results of the other, unfortunately, but we'll make sure we get that out to everybody.
Can you put them in the notes, the results from both polls? And also, will the slides from this apart from the recordings, will the slides be available as well?
Yes, so we will look into that, but for sure the recording will be available in IUPAC YouTube channel. But I'm guessing that also the slides will be available perhaps in the WorldFAIR outlets. So we just want to make sure about that before we just make it public. But definitely we can send you even feedback poll after the result of the feedback poll, as well as perhaps a survey that you can fill in comments, and you know, you can write paragraphs instead of having only multiple choice questions. So we definitely love to have that and provide you with the results of our feedback poll as well. If you have any other concerns or questions, please reach out. I will share with you shortly our contact emails and social media platforms that you could connect with us through. All right, so I think, are we done with the feedback poll, Stuart, now?
We can leave it open. You can go ahead.
Okay, awesome. So once that is running, this is just a reminder for you, for all of our attendees who stayed until this point with us, that this webinar has been already recorded and it will be uploaded on the IUPAC YouTube channel. This is a QR of it that you can also look at into previous IUPAC events, not particularly for the WorldFAIR, but for other, you know, work. And also we have a part 2 of this webinar that it will be what is a chemical, how to or applying chemical data to industrial challenges. Tentatively, it will be in October 13, but it's not confirmed yet. But keep in your mind that we have another coming webinar. Feel free to contact us through our email, follow our social media accounts, especially in Twitter and the IUPAC social media, that all of our news will be always there. Next, we do have upcoming or like open opportunities for everyone who is interested to join our team to advance the FAIR chemical data implementation, either joining our sub-project or sub-project or teams, as I mentioned before, or upcoming spring of 2023, we're going to be having workshops to discuss mainly the deliverables of this project. So if you are interested to be part of this effort, that will be amazing to have you and to have your expertise being also involved in this amazing opportunity. Next, and the last thing I would indicate here, since we have scientists and attendees from across disciplines, the IUPAC has been for many years now celebrating and empowering women achievements, and organizing an event, a global event called the Global Women Breakfast. This is an independently planned event that smaller groups or larger groups can plan. It happens once a year on one day. Next year going to be on February 14. So all women and men are encouraged from across disciplines again, because this year the IUPAC is partnering with the International Year of Basic Sciences and Sustainable Development in this particular event. So the invitation is open for everybody to register and to plan their own Global Women Breakfast. So feel free to visit the website and hopefully to see you there. And if you have any question, please reach out. Even you can reach out to me, as I'm also the coordinator of this project. So at the end, thank you everybody. Thank you for our invited speakers for this amazing opportunity, and you know, giving us your time and efforts to have this event happens at the end. And thank you for all of our attendees for attending from different time zones. Thank you everyone who also planned and organized this event. And we are looking forward to see you in our next occasion. Thank you so much.
Thank you, everybody.
Bye-bye.
Bye-bye. Thank you. Bye.
Thank you. Bye.
Bye-bye.
Bye.
Stop the recording, Stuart.